All right, let's get started with lesson 13, titrations, part 1. Now, a titration is simply an experimental technique that is used to monitor an acid-base neutralization reaction. Now, if you recall, an acid-base neutralization reaction, such as the one with hydrochloric acid plus sodium hydroxide, always produces water and a salt, in this case sodium chloride. So salt will be formed and water will be formed in an acid-base neutralization reaction. And the idea is that in the course of the reaction, all of the acid and all of the base will be completely used up, so there's no more of that remaining, and all that's left is water and the salt that is being made. Now, the titration technique is a way to complete this acid-base neutralization reaction and to monitor the reaction as it occurs. And a typical idea is that we're going to start out with an acid in some kind of container. Usually it's an Erlenmeyer flask or beaker. And we have a certain amount of the acid and base, or the acid in the beaker, and we use a device called a burette, and we'll talk about what that means in a minute. But the burette is going to contain the base, and what happens is we add drop by drop the base into the acid, and we add enough of that base so that it neutralizes all of the acid, so that's what's left is water and salt. Okay, we'll get into more detail in just a bit. Okay, but before we go on with any more with titrations, I want to talk about pH indicators. They are important in the process of using the acid-base titration technique. A pH indicator is a chemical, usually it is a weak acid, that essentially changes colors at various different pHs. Because it changes colors at different pHs, an indicator can be useful to help identify the pH of the solution. Now, there are different ways in which we do this. We can take, for instance, say a test tube here, and we put a acid in it, and we don't know necessarily what the pH of that acid is, so we add a little bit of liquid indicator into the test tube, and that liquid indicator will then change color, and it will change color based on the pH of that acid. And then you look at the color or a scale, and you can see based on that color what the pH would be. Typically something like with this indicator, pHs that are like dark purple are going to be pHs about 14, whereas in the reds and so forth you got pH around 1 to 2 in those ideas, okay, depending on what indicator we're using. Another way to use a pH indicator is to have what are called pH indicator strips. These are pieces of paper that have been dyed with a particular indicator, and when you put the pH strip into the test tube or whatever the container the acid or base is in, so we'll say acid here, that pH strip is going to change color, and then you take that colored strip and compare it to a chart that has the different colors that indicate what pH is in. And you just compare the paper to the chart, and that will tell you the pH of the solution. So it's a nifty way of determining the pH by using these indicators. And so you can use either method, either the liquid drops or the pH indicator strips. In selecting the appropriate pH indicator for a particular reaction or titration, what we need is a indicator chart like the one that's listed here. The indicator chart gives us a list of different weak acids that change color in the presence of different pH solutions, essentially. For instance, Thymo Blue here, which is the first one, changes colors at various pH ranges. So at a pH of essentially, you could say 0 to 1, it's a pink color. By the time it's just over 1, and before it hits a pH of 3, it will have a kind of a darker orange color. But from a pH of about 3 to pH of 8, it will have a yellow orange color associated with it. And then once it turns to a pH of 8, the solution will then change color to a light blue until about a pH 9, and then it will remain dark blue all the way to a pH of 14. So by knowing these colors for this particular indicator, then you can kind of monitor where the pH is at based on adding an acid or base to our solution. All right. So for instance, let's go ahead and say we have an acid solution here. And initially, when we put in our Thymo Blue indicator, it is a pink color. So that would tell us that roughly our pH is going to be between a range of 0 to 1. And then let's say we start adding into this drop by drop a base. Okay, so that should start causing the pH to increase once we begin to add that base. And then acid-base neutralization reaction should begin. All right, so as the pH increases, when it starts getting into a pH between 1 and 3, then the color of our solution should... Oops, I just lost my diagram here. So let me really quick re-diagram this. So again, we have our acid solution. We're going to add our base into our acid, and by doing that, the pH should begin to increase, and that should mean that as we're increasing with the indicator inside of the acid container, the color should be changing. So by the time it's at between a range of pH of 1 and a pH of 3, it should be that darker orange. By the time it gets to a pH of 8, by adding enough base, it should really become kind of a light blue color. So hopefully you kind of get the idea about how these indicators work as we add the base to the acid and increase the pH there. All right, so that's it as far as indicators right now. In class, we'll play around with some indicators and kind of get more familiar with them and their uses. All right, so let's go back to acid-base titrations. As far as the technique is concerned, there's a couple very important vocabulary words that you need to understand when it comes to a titration. The first one is known as the equivalence point. The equivalence point, by definition, is the point that is reached during a titration in which the original amount of both the acid and the base has been completely used up. So if you think about our strong acid, strong base neutralization reaction here with water and our salt, when the equivalence point is reached, it should be when all of the acid and all of the base has been completely used up. They're both going to be limiting at that point. So there should be nothing left of them, no excess of either the acid and the base. So the only thing that should be in our solution at the equivalence point is water and the salt. All right, so kind of think about it in this terms here. Let's say that we have again, a container of acid, and we're going to add our base to the acid. And at first, the acid is going to be excess because there's a lot more acid than base when we add drop by drop. But over time, as we add more and more base, the base is going to use up more and more acid. So again, you can think of, as far as stoichiometry is concerned, the base initially is the limiting reactant, and it will be completely used up and use some of the acid, but for the most part, the acid will be in excess. But as you use more and more base, you begin to eliminate more and more of the acid till you reach the equivalence point. And once the equivalence point is reached, there will be no more acid, and all of the base that was added is also completely used up. So all that's left in our solution container is going to be water and the salt. Okay? And you're going to essentially, that's kind of the gist of the idea in a titration, is to reach that equivalence point so that there is no more acid and base. The other vocabulary word that's important is known as the end point. The end point is reached during the titration, in which the indicator that we've added changes to the desired color and pH, indicating the end of the titration. So essentially, the end of a titration occurs when we hit the end point, which makes sense. And the end point essentially is reached when we know that the indicator changes color to the desired color that we're looking for. Now, the key to a titration is to have the essentially what we would like is to have the end point and the equivalence point be the same. All right? So in other words, that as soon as we hit the equivalence point, the indicator changes to the correct color we're looking at, and then indicates that we've basically hit that equivalence point, and therefore we can stop the titration. All right? But the only way to do that is to choose an indicator that will change color at the correct endpoint to give us the equivalence point. Hopefully that makes sense. Okay, I think it will as we look more at the titration technique here. So here is the basic setup of a titration. This diagram is in your study guide here. All right, the basic idea is we're going to use a glass burette. This glass burette is usually a long, thin tube that basically has graduating marks on it, volumetric marks on it, to measure volume in it. And essentially, usually, the burette is going to have the base, sometimes the acid. So you usually put the base inside of the burette, and therefore with the graduated volumetric marks on it, you can determine the amount of base that is in the burette. All right. Now, the acid is usually placed in some kind of glass container. Usually it's an Erlenmeyer flask. Sometimes it might be a beaker. With the acid, we also put the indicator. Now, once in a while, if we put the acid into the burette, then we'll put the base in the Erlenmeyer flask. But typically, the acid is in the Erlenmeyer flask, the base is in the burette. Now, the burette has a stopcock on it, so that way it does not allow the volume to escape into the volumetric flask until you want it to do so. And so as soon as you want to start adding base to the acid, you basically move the stopcock to allow the acid to, or base to begin to start dripping into the acid, and the titration will begin. All right. Normally, in a titration with the burette, you will definitely know the quantity of base, and you'll know the concentration of the base, but you may not know the concentration of the acid, just the volume of the acid that was used. Okay, we will actually do an experiment with an acid-base titration in this manner, so you can practice this technique and learn how to monitor a acid-base neutralization reaction with a titration. All right, so this is kind of, again, the setup. Our flask here, we're going to put in this case, we're going to pipette 20 milliliters of the acid into our flask. We're going to put the base, sodium hydroxide, into our burette. We're going to read the initial volume of the burette so we know how much base is in there. And then we're going to just begin to add base into the acid solution. Now remember that the pH indicator is in the burette, or in the flask, so it can change colors once we hit the end point. And as you can see, that as we continue to add base, we finally get a color change that we want. So we've reached the end point, which we hope again is the equivalence point, and so that all of the acid and base has been neutralized at that point. And so then we know what the final reading of the burette is. So essentially, some important measurements to make is going to be the initial volume of the base, and then the final volume of the base that was added. These two measurements right here are critical in doing a titration. The other measurement that's critical in the titration is knowing the original amount of acid that you added, the original volume of acid that you added to the flask. Okay, so keep that in mind as you do titrations. All right, so here you can see the kind of the progression of the titration. Initially, this is the start of the titration, where we have not added base yet. There's base in the burette here, and when we open up the valve, we'll allow the base to drip into the acid here to begin the titration. Notice that initially, once you add base, you're going to get a little bit of color change due to the neutralization that occurs. That color change, though, will disappear once all the base has been used up, because it is the limiting reactant. And then you're going to continue to keep on adding more and more base, drop by drop, until eventually the color is changed completely and you hit the end point of the titration, which we hope again is equal to the equivalence point. Where the acid and base is completely used up. Here we look at it again. We have the start, we have during, with a little bit of color change based on the indicator, and then we have the finished titration, where we've hit the end point again. Okay. So anyway, that's kind of the idea of the titration technique and doing so. Again, the initial volume of the acid, so we want the volume of the acid. We need to know that. We need to know the start starting volume of the base, and then we need to know the ending volume of the base. Those three important measurements must be taken. All right. So now what about the calculations? Okay, the calculations are not too bad when you're dealing with a titration like this, because they're essentially acid-base neutralization reactions. So for instance, let's take a quick look at 3 example problems. We'll go quickly. We're going to calculate the concentration of a 25 milliliter HCl solution. If it took 50 milliliters, that's the total volume of a strong base that has a concentration of 1 molar to use up all the HCl. So again, what we're having is we're going to take the HCl and we're going to add sodium hydroxide to it until we've all neutralized it. All right, so essentially you could look at, we have 25 milliliters of the HCl, and we're going to add in base. Total amount of base through the titration will be 50 milliliters, and then we'll reach our end point, and that will be our neutralization point there, or equivalence point, we should say. Okay, so let's look at the math. All right, so the first thing we need to do is, once we know the total volume of the base added and we know the concentration of the base, we can use that to find the number of moles that we actually added to the acid solution to neutralize it. So a 10 molar sodium hydroxide solution, we're going to multiply that by the volume added, which is going to be 0.050 liters. And that gives us 0.05 moles of sodium hydroxide, or the base added, to neutralize all the acids. So again, this is the moles that was needed to neutralize the acid. Well, therefore, since the ratio, stoichiometrical ratio between the sodium hydroxide and the HCl is a 1-to-1 ratio, and we're using up all of the moles of base to create the essentially, which is equal to the moles of acid in that 1-to-1 ratio, we can say that the 0.05 moles of sodium hydroxide over 1 times the stoichiometrical mole ratio, 1 mole of HCl to 1 mole of sodium hydroxide, tells us then we have 0.05 moles of hydrochloric acid. So that's the number of moles that we started in our flask, all right, before we started adding base, all right? So in the 25 milliliters, so essentially, again, we have 25 milliliters of the acid, which is HCl. We also now know that the concentration, or the number of moles, we should say, is 0.05 moles of HCl. All right. Now we can use that to find the concentration by taking the number of moles of HCl dividing by the volume of HCl initially, which was 25 milliliters. So that would be 0.025 liters, and that will give us a concentration of 2 molar. So that means our original acid concentration was a 2 molar HCl solution. And that's what it was before we added the base. Okay, so that's essentially how we deal with a strong acid and strong base titration calculation in this case. All right, let's do another one. This one, we haven't quite reached the equivalence point or the end point in this one. We want to calculate, in this case, the pH of our solution if we've only added 49 milliliters of a 0.1 molar sodium hydroxide to 50 milliliters of a 0.1 molar hydrochloric acid solution. So again, our reaction will be the same: strong acid, strong base, neutralization reaction here. Form our salt. right? So initially, the HCl has a concentration of 0.10 molar. We're going to multiply that by the volume of HCl, which is 0.050 liters, and that gives us a number of moles of HCl. That's how many moles of HCl we have in our solution. Now the base that was added, we had a concentration again of 0.1 molar, and then the added base is we only added 0.49 liters, which gives us the number of moles of 0.0049 moles of sodium hydroxide. Now, since sodium hydroxide and hydrochloric acid react in a 1-to-1 ratio, it tells us that we have an excess amount of hydrochloric acid, because if we had neutralized all of the acid and base, the moles of acid and base should be equal here, but they're not. So we still have, so our limiting reactant is the base, and our excess reactant is hydrochloric acid by 0.0010 moles, okay, essentially. Or, sorry, didn't do my math correct. I need to retract that. So it'd be 0.0001 moles excess, HCl in excess. That hasn't been used up completely. I need to add just a little bit more base to use up all the acid. So we haven't actually reached the equivalence point at this time, okay? So what is the pH? Well, since this is a strong acid, this should also be the amount of hydronium ion that would exist in our solution at the time. So we're going to take our 0.0001 moles, and we're going to essentially divide it by the total volume of the solution, okay? And the total volume of the solution is essentially 50 milliliters plus 49 milliliters. So that should give us a 0.099 liters, which gives us a concentration of essentially 0.0010 molar of the hydronium ion. Okay, so then we plug that into our pH equation. So the pH is equal to the negative log of 0.0010 molar, and therefore it gives us a pH of 3. So we are basically a milliliter away from hitting the equivalence point, and it is still only a pH of 3. All right, so that's pretty significant. So if we add another milliliter of base, we should neutralize all the acid, and the pH should then become a pH of 7. So just that little bit of a difference is pretty significant on the overall pH. All right, so that is example problem 2. The last example problem that we have is kind of the other way of thinking here, where we're going to have an excess now of base, and we've used up all of the hydrochloric acid. So HCl plus sodium hydroxide produces water plus the salt. Rewrite that, sodium chloride. Okay, so now what we've done is we've added essentially for the HCl, we had initial 0.0 liters of it times a 0.10 molar solution, which gave us our initial 0.00050 moles. And then for the base, this is what we add. we added 0.051 liters, okay, just a little bit more over the equivalence point. So we added just a little bit more base, 0.01, right? So we would assume that our pH is probably going to be greater than 7 since we've overshot the equivalence point. We now should have more base than we have acid, indicated by the number of moles. So when we subtract that, we have 0.0001 moles of excess base now added to our titration. So before we didn't have enough base, and now we have more base to make it excess, right? So what is our new base concentration? 0.0001 moles divided by the total volume that we have here, which is 0.101 liters. So that gives us, if we do a quick calculation, should give us a concentration of 9.9 times 10 to the minus 4. All right. Now, this should be our base concentration or our hydroxide concentration. So we can't find the pH directly, but we can find the pOH is equal to the negative log of 9.9 times 10 to the minus 4. And so if we take the negative log of that number there, to do a real quick calculation, we find that the pOH should equal 3. All right, so if we want to find the pH, remember pH plus pOH is equal to 14. So 14 minus 3 will give us our answer, which is going to be 11. So it tells us that by just overshooting the overshooting the base by 1 milliliter, it drove our pH from 7 to a pH 11. So remember, we would think that if we had equal amounts of acid and base at the equivalence point, the pH should be 7. But since we have a little bit of excess base, 1 milliliter of it, it drove the pH clear up to 11. Okay, so these are the calculations that we would take for a strong acid, strong base titration you would look at. All right, so this is it for part 1. Make sure you study these notes really closely. Titrations are very important. Come to class with questions, and we'll have plenty of problems to solve, as well as we will be doing some lab work relating to acid-base titrations.